Locomotives built in the 1970s are still hauling freight today, while million-dollar modern units sit idle in storage yards, a paradox that makes no financial sense on the surface. Why would the world's largest railroads deliberately keep machines that are 40 and 50 years old running when newer, cleaner, more efficient models exist? The answer isn't nostalgia. It's a calculated strategy built on rebuild economics, regulatory loopholes, and one legendary engine platform that the industry has tried and failed to replace. Class 1 railroads manage some of the most capital-intensive networks on Earth, where every investment is scrutinized through a lens of strict utility. A single modern freight locomotive carries an upfront price tag of roughly $3 to $4 million. For an industry that measures profit margins in fractions of a percent, buying new is never the default option. Instead, fleet managers evaluate assets using a total cost of ownership framework. This model weighs initial capital expenditure against daily operating costs, long-term maintenance, and the revenue lost when an engine sits in a repair shop. The decision-making process is entirely clinical, driven by spreadsheets and line-item realities rather than any sentimental attachment to historic machinery. Under this math, a locomotive is not judged by its age or technological sophistication, but by its availability and reliability. A highly computerized, fuel-efficient unit is only valuable if it is moving freight. If a newer locomotive requires specialized electronic diagnostics that sideline it for days, its theoretical efficiency vanishes. Conversely, a simpler, older machine that achieves high availability can be far more profitable, even if it burns slightly more fuel. This reveals what railroads are actually optimizing for. Railroads seek the lowest cost per mile of reliable tractive effort rather than technological novelty. On high-volume mainline corridors, where trains run thousands of miles uninterrupted, the fuel savings of a modern engine can justify its capital cost. But on secondary lines, local runs, and branch lines, the operating equation flips. In these environments, utilization rates are lower, and locomotives spend hours idling or switching cars at low speeds. Here, the priority shifts from maximum fuel efficiency to minimizing capital depreciation. Keeping a $4 million asset underutilized on a branch line is an economic failure. Utilizing a paid-off, easily repaired asset is an operational triumph. The corporate math of asset utilization finds its clearest real-world application in a single model, the Locomotive Division, SD42. Built between 1972 and 1986, this six-axle diesel-electric locomotive became the absolute backbone of North American railroading. General Motors produced 4,029 units for the domestic and Canadian markets, establishing an industrial footprint so massive that it structurally altered how railroads handled fleet logistics. Today, 50 years after the first units rolled off the LaGrange assembly line, hundreds of these machines remain in active, revenue-generating service. This single model turns the broad question of locomotive retirement into a specific, concrete case study. The longevity of the SD42 stems from an aggressively simple, no-frills design philosophy, rather than corporate nostalgia. At its core lies the EMD 600 E3 prime mover, a turbocharged, two-stroke, 16-cylinder engine producing 3,000 horsepower. Mechanics refer to this engine block as virtually unkillable and cheap to rebuild. EMD paired this rugged power plant with the -2 modular electrical system. Instead of the complex, hardwired circuits of earlier generations, the SD42 introduced standardized plug-in circuit cards. If an electrical fault occurred, shop crews could swap out a card in minutes, rather than spending hours tracing individual wires. This modularity turned the SD42 into a highly standardized industrial platform. Railroads could pool parts, streamline training, and establish uniform maintenance practices across thousands of miles of track. The heavy steel chassis, the high-torque D77 traction motors, and the HTC trucks provided a starting tractive effort of 115,000 pounds. It was a machine built to tolerate extreme weather, poor track conditions, and heavy loads with minimal unscheduled downtime. The Locomotive became the benchmark against which all subsequent designs are measured, proving that reliability is a function of simplicity and repairability. The acquisition of locomotive power is governed by the principles of large-scale fleet asset management. Class 1 railroads do not treat locomotives as individual acquisitions. Instead, they manage them as massive, interconnected portfolios where standardization dictates profitability. This commercial market is defined by extreme consolidation, historically dominated by two major builders, General Electric, now Wabtec, and the Electromotive division, now Progress Rail. This duopoly shapes the operational environment of North American railroading. The dominance of these manufacturers determines which mechanical platforms exist, which components remain in production, and which systems can be economically supported across a continent-spanning network. When a railroad introduces a locomotive class, it commits to a massive long-term infrastructure of parts distribution, maintenance facilities, and technician training. Because of these high structural barriers, supportability is the primary factor in any purchasing decision. Introducing an entirely new mechanical platform creates a massive logistical burden, requiring new diagnostic tools, different spare parts inventories, and specialized mechanical training. Railroads prioritize keeping their existing support networks active rather than constantly introducing new platforms. They approach fleet planning with a focus on roles rather than novelty. Every locomotive is assigned to a specific tier of service, ranging from high-speed mainline transit to secondary local runs and low-speed yard switching. Rebuilding an older locomotive is a standard, highly structured option within the normal decision set of a railroad's capital allocation program. Fleet managers continuously weigh the return on investment of a new purchase against the remanufacturing of an existing chassis. The decision is entirely functional. If an existing platform can be upgraded to reliably perform its assigned role within the established maintenance ecosystem, extending its life is a primary strategic pathway. In a mature, capital-intensive industry, asset utility and system compatibility always override the appeal of the new. Modern locomotives operate as rolling computer networks, where thousands of sensors continuously monitor emissions, wheel slip, and engine parameters. When a single sensor fails on a high-tech unit, the onboard computer often triggers a protective derate, cutting horsepower or sidelining the train entirely until a technician connects a proprietary diagnostic laptop. On a remote siding, this digital sensitivity is an operational liability. Older platforms operate on a largely physical philosophy. These machines rely on mechanical linkages, heavy pneumatic valves, and copper contactors rather than microprocessors and software loops. The governor regulating engine speed is a hydraulic and mechanical device, not a digital controller. The electrical system uses analog pathways that a mechanic can troubleshoot using a standard multimeter. This lack of software layers directly changes how maintenance happens. In a remote yard, a shop crew can diagnose a fault through physical inspection. If an electrical contactor sticks, it can be cleaned or manually overridden. If a fuel line leaks, it can be repaired on site. There are no software-induced lockouts or sensor-driven shutdowns that require factory IT support to clear. The locomotive functions as an open, repairable industrial tool rather than a sealed black box. For railroads, this forgiving architecture means faster troubleshooting and reduced downtime in the field. When a locomotive operates in extreme cold, heavy dust, and constant vibration, physical toughness becomes more important than digital systems. In everyday service, a machine that a local crew can repair with basic hand tools will always outlast a more advanced platform that is too complicated to fix on the spot. When a mechanical platform operates for 50 years, it ceases to hold any surprises. Every structural weakness, every thermal stress point, and every electrical vulnerability has already occurred thousands of times across the rail network. For a railroad, this exhaustive history transforms maintenance from an exercise in emergency troubleshooting into a predictable routine. A fleet manager operating these legacy units is not managing a perfect machine. They are managing a known set of failure modes. If a specific component on an older engine tends to fatigue after a certain number of operating hours, that threshold is recorded in decades of shop logs. The railroad knows exactly when to replace it before it fails on the main line. Maintenance teams do not have to guess where a leak might develop or why an engine might lose power. They have 50 years of collective experience pointing to the exact gasket or valve. This predictability is a major advantage in risk management. A brand new, highly computerized locomotive represents an operational gamble. No matter how extensive the manufacturer's pre-production testing, real-world service in sub-zero winter temperatures or desert heat eventually reveals unexpected flaws. Software anomalies, sensor failures, and structural micro-cracks in untested components can sideline a new fleet without warning, disrupting entire shipping corridors. By contrast, the risks associated with older units are fully quantified. Railroads build their operational schedules around these known variables. Institutional trust is not about believing a machine will never break. It is about knowing exactly when and how it will break, and having the tools, parts, and training ready to address it instantly. The core of this strategy comes down to a straightforward financial calculation. A brand new Tier 4 locomotive costs approximately $3.2 million. For a railroad looking to expand or refresh its haulage capacity, buying a fleet of these machines requires a massive capital commitment. A rebuilt unit, by contrast, offers a far lower barrier to entry. Stripping a locomotive down to its frame and rebuilding it from the ground up typically costs between $1.2 million and $2 million. Major Class 1 carriers routinely spend in this range on their modernization programs. This route delivers a direct capital savings of up to $2 million per unit compared to purchasing new. With these figures on the table, the central engineering and financial question for a railroad fleet manager becomes simple. Does the existing steel frame still have enough structural life left to justify the investment? A locomotive frame is a massive, heavy piece of structural steel. Unlike the engine, electronics, or traction motors, the frame itself does not have moving parts to wear out. If the frame is straight, free of major fatigue cracks, and structurally sound, it can serve as the foundation for a rebuilt locomotive that performs with the high availability of a new machine at a fraction of the cost. This is not a choice driven by nostalgia. It is a cold calculation of asset life and capital discipline. The economics are strongest when a railroad needs dependable horsepower to move tons of freight, rather than a prestige purchase. By rebuilding an existing asset, railroads extend the service life of their fleet for another 20 years while keeping millions of dollars on their balance sheets. Older locomotives continue to work the rails because when evaluated under strict accounting rules, they simply pencil out. The decision is a practical step to secure the best return on every dollar of capital spend. In a highly competitive transportation network, utility will always triumph over novelty. A machine is only as viable as the supply chain supporting it. Because EMD built thousands of these locomotives, an entire secondary industry grew to keep them running. This aftermarket network relies heavily on the interchangeability of standardized parts. Mechanics can strip a retired unit in a salvage yard and use its traction motors, wheel sets, or electrical contactors to revive an active sister unit. Original manufacturers like Progress Rail support this massive installed base through specialized programs, offering refurbished components such as Econolife power assemblies. This level of standardization ensures that maintenance shops do not have to wait for custom-engineered components when a unit fails. They work with a known mechanical platform where parts swap cleanly and fit perfectly. However, this vast parts pool is not entirely immune to friction. While common gaskets and valves remain plentiful, major legacy components can face significant bottlenecks. For hard-to-source items like specialized cylinder liners or crankshaft assemblies, railroads often face lead times extending to 120 days. To offset these delays, railroads rely on the extensive institutional knowledge of their workforce. Generations of diesel mechanics have spent their careers working on the 645 prime mover. They know its tolerances, its structural vulnerabilities, and its mechanical quirks by heart. This human expertise is as valuable as the physical hardware itself. When an engine arrives at the shop, mechanics diagnose and repair failures without consulting proprietary software or waiting for factory technicians. The entire rail network has spent 50 years learning how to keep this specific machinery alive, creating a self-sustaining ecosystem that resists obsolescence. The push for cleaner air altered modern locomotive design, turning a quest for raw mechanical power into an exercise in chemical engineering. To meet modern Tier 4 emission standards, manufacturers had to install massive after-treatment hardware directly into the locomotive car body. These systems use selective catalytic reduction and diesel particulate filters, requiring complex plumbing, chemical dosing pumps, and a continuous supply of diesel exhaust fluid. But treating high-volume diesel exhaust under harsh operating conditions is an energy-intensive process. The back pressure from restrictive particulate filters, combined with the active thermal management required to burn off accumulated soot, introduces a highly counterintuitive trade-off. Instead of saving fuel, these advanced emission systems impose a fuel economy penalty of roughly 6% compared to the Tier 3 locomotives that preceded them. This added machinery creates a dense network of physical and digital failure points. In hard freight service, where locomotives endure constant vibration, freezing winters, and desert heat, these delicate systems easily break down. Software glitches, urea pump failures, and sensor drift frequently trigger automatic horsepower derates to protect the emissions hardware. A locomotive designed to be cleaner on paper can quickly become an expensive operational liability, sidelined not by a mechanical failure of its steel prime mover, but by a clogged filter or a faulty sensor in the exhaust stack. This is the central irony of modern fleet complexity. While advanced emissions controls successfully reduce local pollutants, they introduce a steep maintenance, diagnostic, and operating burden. The technology is not a failure of engineering, but it represents a clear operational trade-off. Cleaner in practice does not automatically mean easier to run, and the added vulnerability of these complex systems makes the uncompromised simplicity of legacy power increasingly difficult for railroads to abandon. The survival of 50-year-old locomotives is shaped by federal law. When the Environmental Protection Agency introduced its tiered emissions framework, it created a regulatory structure that changed how railroads managed their assets. Starting in 2000 with the introduction of Tier 0, Tier 1, and Tier 2 standards, and moving through the implementation of Tier 3 in 2011, regulators steadily tightened limits on diesel exhaust. By 2015, the agency made Tier 4 standards mandatory for all newly manufactured locomotives, requiring an 80% reduction in particulate matter and nitrogen oxides, along with a 70% cut in hydrocarbons compared to Tier 3 baselines. This policy shift presented railroads with a clear choice. Every brand new locomotive purchased had to comply with these rigorous standards. However, the legal framework contained a distinct set of rules for existing equipment. Under federal guidelines, when a locomotive undergoes a major rebuild, it is subject to the standards associated with its original year of manufacture, rather than the standards of the day it leaves the shop. for the massive fleets of locomotives built after 1973. This meant a rebuilt unit only had to satisfy Tier 0, Tier 1, or Tier 2 standards. This legal mechanism, known as the remanufacturing rule, created a powerful economic incentive. Instead of purchasing a new $3 million Tier 4 unit, a railroad could choose to overhaul an existing locomotive to an older, far less stringent standard. As a result, the regulatory rulebook became a structural driver of fleet strategy. Fleet managers began evaluating their rosters through a legal lens. The primary question shifted from mechanical repairability to legal compliance, prompting railroads to evaluate whether an existing frame could remain in service lawfully. Because the heavy steel frame holds the original manufacturer's date plate, it serves as the legal anchor for the locomotive's emissions tier. By maintaining and rebuilding these older frames, railroads legally bypass the requirement to adopt complex Tier 4 emission systems. Regulators defined the boundaries of the commercial market, creating a policy environment that rewarded strategic rebuilding. The rulebook, designed to clean the air, became part of the locomotive's survival logic, extending the lives of the very machines it sought to replace. The physical manifestation of this regulatory strategy takes place on the shop floors of massive heavy repair facilities like Union Pacific's Jenks shops in North Little Rock, or Norfolk Southern's Juniata shops in Altoona. Here, the process of remanufacturing is not a simple repair job, but a systematic industrial transformation. Technicians strip a retired locomotive entirely down to its bare steel frame. This frame, a massive piece of welded structural steel designed to withstand millions of pounds of compression, has no moving parts to wear out. Because the frame carries the original manufacturer's builder plate, it serves as the legal anchor for the locomotive's identity and its emissions tier. By keeping the original frame, railroads can legally renew the entire operating core of the machine without triggering the requirement to meet modern Tier 4 emission standards. The engine, traction motors, and electrical systems are removed, but they are not discarded. Instead, the remanufacturing process exploits an efficient closed-loop supply chain where up to 90% of the locomotive's physical material is recycled, refurbished, and reinstalled. The heavy steel chassis is blasted, inspected for microstructural cracks, and reinforced. The EMD 645 engine block is line-bored, fitted with refurbished power assemblies, and lowered back into the frame. Traction motors are rewound, and the cab is often completely replaced with modernized, crash-worthy designs like Norfolk Southern's Admiral cab. This mechanical rejuvenation turns what was once retired equipment into a renewed, high-availability asset. It provides railroads with a machine that delivers the reliability of a brand-new unit while saving up to $2 million per locomotive over a new purchase. This is not an experimental or niche practice. It is a standard, capital-intensive strategy deployed at an immense scale. Union Pacific's $1 billion program to modernize 600 older locomotives, alongside CSX's extensive SD-43 and -3 initiatives, demonstrates that rebuilding is a core pillar of North American fleet management. The specialized rebuild shops and aftermarket suppliers function as the hidden industrial engine of the rail network, proving that the most cost-effective way to secure the future of freight transit is to rebuild its past. Railroads do not demand the same performance from every locomotive in their fleet. A long-haul mainline run requires raw horsepower and maximum fuel efficiency, but secondary lines, branch runs, and yard switching operate under entirely different economics. On these secondary tracks, trains run at lower speeds, travel shorter distances, and spend hours idling. Placing a brand new $4 million locomotive on a local branch line, where it sits idle for half the day, is an inefficient use of capital. Instead, fleet managers match machine age directly to operational demand. This role assignment is where older rebuilt units like the EMD SD42 find their modern purpose. While a 50-year-old locomotive cannot compete with a new AC traction unit on a transcontinental route, its six-axle design and starting tractive effort of 115,000 pounds make it perfect for yard work. In places like CSX's classification yard in Montgomery, Alabama, or BNSF's hump yard in Galesburg, Illinois, raw pulling power and physical reliability are far more important than high-speed efficiency. Moving massive cuts of freight cars up hump tracks requires heavy, durable steel frames that can tolerate constant stopping, starting, and low-speed shoving. To further adapt these yard operations, railroads often retrofit these older units with remote control equipment during overhauls. This allows a single crew member to control the locomotive from the ground, turning a vintage road switcher into a highly efficient yard tool. Shifting these older units to low utilization roles extends fleet service life while acknowledging the real-world costs of age. These secondary duties do not demand the tight tolerances of high-speed mainline service, allowing the railroad to minimize capital depreciation while maintaining high availability. The legacy locomotive becomes an asset dedicated to low-speed, high-torque tasks, proving that long-term profitability relies on placing the right machine in the right role. The operational limits of legacy equipment become apparent on high-volume mainline corridors. Here, the fuel economy penalty of older locomotives becomes an unsustainable operating expense. Under comparable heavy loads, a classic SD40-2 consumes roughly 10 to 15% more fuel than a modern microprocessor-controlled line haul unit. When a locomotive operates 20 hours a day, pulling thousands of tons across transcontinental routes, this efficiency gap translates into hundreds of thousands of dollars in wasted fuel annually per unit, erasing any upfront capital savings. Modern high-adhesion alternating current traction systems deliver pulling power that older direct current motors cannot match. A single modern alternating current locomotive frequently replaces two older direct current units on heavy coal or grain trains, reducing crew costs, maintenance overhead, and track wear. In these demanding mainline profiles, purchasing new equipment is an operational necessity. From an environmental perspective, older rebuilt locomotives meet only Tier 0 to Tier 2 standards, failing to achieve the 80% reduction in particulate matter and nitrogen oxides mandated for modern Tier 4 power. In air quality sensitive regions, operating legacy units can trigger substantial compliance fees and regulatory restrictions. As local regulations tighten, the cost of retrofitting supplemental emission controls onto older engines quickly exceeds the value of the locomotive itself. The physical process of rebuilding also faces unyielding limits. Every locomotive frame has a finite structural fatigue life. Decades of pulling millions of tons of freight, enduring extreme thermal cycles, and absorbing coupling impacts eventually fatigue the thickest structural steel. Most locomotives can only undergo a maximum of 3 major remanufacturing cycles. Beyond this threshold, metal fatigue and corrosion of the core frame make further overhauls unsafe. At this stage, each subsequent rebuild yields diminishing returns. The machine reaches a point of absolute physical obsolescence, where mechanical repairs can no longer stave off the scrap heap. The economic logic of the railroad dictates that when the frame's structural integrity fails, the asset must be retired. The strategy is not about preserving old technology at all costs, but about recognizing exactly where old engineering meets its physical and economic boundary. Today, the survival of these steel workhorses is a masterclass in industrial pragmatism. As railroads navigate pressure to decarbonize, this rebuild culture faces an inevitable clash with stricter environmental limits. Yet for local yards and short lines, the cold math still favors mechanical simplicity over complex software. In an industry obsessed with the next high-tech solution, the most valuable machine remains the one that refuses to break down. What do you think? Share your thoughts below.